This recording is covering electron configuration. When we think of electron configuration, we're talking about an atom. And everything we're talking about in chemistry, we're thinking of a system. And for any system to work, it needs to be energy efficient. And what do I mean by that? It means that the amount of energy going in should be less than the amount of energy that's coming out of the system. So in terms of atoms, we are thinking of the idea that atoms are going to place their electrons in a certain distance away from their nucleus that allows them to be energy efficient. So what we know is that electrons can be found in something what we call principal, I might be spelling this wrong, energy levels. And closest to the nucleus, we have n equals 1, n equals 2, and n equals 3. Now, for the Bohr model, you see we have the shells surrounding the nucleus. And if we want to know the number of electrons in each shell, is going to be equal to 2n squared, where n is the principal energy level. I think it's principal. That's what I'm going to go with. Sorry, guys. Principal energy levels. Okay. So if we want to know for n equals 1, that's going to be 2 times 1 squared is 2. So we have two electrons in energy level 1. And being that things have to be energy efficient, it's most efficient to have those electrons as far apart from each other, because you know that electrons are negatively charged, so they will repel each other if they're too close. So if we're thinking about the next energy level, we see that we are able to put 8 electrons. And in energy level number 3, we are able to put 18 electrons. All right. So for ease, I'm just going to show electrons in energy level number 2. All right. Now, that's the Bohr model of the atom. If we're thinking about the quantum model, well, we have the energy levels are broken down into sublevels, which then house orbitals. And this is a simplified version of the quantum model, but we'll take a closer look at each of these. Now, mind you, the electrons will be found within the orbitals, which is a probability in space where electrons would be located. So it's a three-dimensional probable location for electrons in a given orbital or in a given, let's say, sublevel. Now, the farther we move away from the nucleus, the electrons are higher and higher energy. As I mentioned in class, if we think of the atom as a mama, and electrons that are closer to the nucleus would be those electrons that, or the children that would be held on by their mom, by their hand, right? The farther we go away, these electrons have more and more energy, and they have more and more roam. They can, well, they're located in a different. As we move away from the nucleus, electrons have higher and higher energy. And we know this from electromagnetic radiation studies. Okay, so let's take a closer look at these energy levels and how they relate to our periodic table. So if we take a look here at our periodic table, we can see here that we have our energy levels. And notice that these principal energy levels relate to the periods on the periodic table. And you notice that the energy levels increase as we go down the periodic table. Okay? Now, if we want to take a closer look at where these electrons reside, let's use an analogy that can help us to think of how the sublevels and the energy levels are broken up. Let's say we were to represent the atom as a house. And as we go up this house, don't make fun of my house. But as we go up the floors on the house, each floor is going to represent an energy level. So here we are on the first floor. Here we are on the second floor. And here we are on the third and the fourth floors. All right. So remember, N are the energy levels. And let's say down here is the nucleus. All right, in the basement. On each level, we have a room, and each room has a name. And each room is going to be considered a sublevel. So we have sublevels, and those are going to be the rooms on the floor. Now, these floors are special because each room or each floor has the same number of rooms that equals the number or the floor. So on the first floor, we've got one room. Second floor, we've got two. We'll describe the rooms as we go. So within that room now, let's say there's a bed in that room, and that bed is going to represent an orbital. Now, in the bed, there's special rules in the house where you can only fit 2 people in the bed, and they have to lie foot to head. So people, sorry for the dog, are our electrons. All right, and they have to go in foot to head. Well, it makes sense because electrons are negative, and so they have to have opposite spins so that they can live in the same location. All right, so notice that we can put 2 electrons on the first floor. When we go to the second floor, there's also an S room with an S bed. And we also have a P room with P beds. And I'm not going to draw the P rooms with the P orbitals as they would look, because, well, let's try. I'm not sure if you will be able to see the electrons when I'm done, but we'll try. Let's see if we can get some P orbitals in there. All right. So if we remember orbitals, they can only have 2 electrons apiece. So we can have 2 electrons in the s orbital. Let's see if I can. 2 electrons in a p orbital, 2 electrons in this p orbital, and 2 electrons in the last p orbital. As we go to the third floor, we have an s room, a p room, and a d room. Now, in the s room, we've got s orbitals that we know can hold 2 electrons. We've got those p orbitals that each orbital can hold 2 electrons. And we've got d orbitals, and I'm just going to draw those as weird rectangles. And remember, for each orbital, you can put 2 electrons. Okay? So on the fourth floor, we've got a S room, a P room, a D room, and an F room. And we've got an S bed, 3 P beds, 5 D beds, and we've got 7 F beds. Okay? And I won't draw the electrons in the top, but you'll see. So notice we have how many electrons here on the first floor? How many electrons can be held on the second floor? Right, 8 electrons. How many total electrons can be held on the third floor? And if you do all the math and add everything up, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we have 32 electrons that can go in the fourth energy level. Now remember, I was giving these names. So notice the sublevels have names S, P, D, and F. The orbitals also have the same name. All right, so you will only find s orbitals in a s sublevel. You will only find p orbitals in a p sublevel. You will only find d orbitals in a d sublevel, and so forth and so on. Now, let's think about these sublevels, and let's write out a plan based on what we were looking at on our periodic table. Let's make a table, and we're gonna look at the energy level, we're gonna look at the sublevel, we're gonna look at the orbital, and we're gonna look at the number of electrons. All right, on n equals 1, we have one sublevel, it's called a s, and we also have one s orbital, and we can have 2 electrons in that s orbital. When we move to the second energy level, notice that we have an s sublevel and a p sublevel. Here we have 2 s orbitals, and we had, how many did we have in our house? We had 3 p sublevel, p orbitals, excuse me. And we can have a total of 8 electrons. On the third energy level, we have s sublevel, we've got the p sublevel, and we've got the d sublevel. If you remember, we had, let me go back up here. There's 1 s sublevel. Let me fix that. Okay. Now, back up here, back down here to the third energy level, we have 1 s sublevel. We've got 3, pardon me, we've got 1 s orbital. We're talking about orbitals. We've got 3 p orbitals. And if you remember, how many beds did we put in the house on the d level? In the d sublevel, we had 5 d orbitals. And if we remember, we had 18 electrons. If we move now to the fourth energy level, we've got an s orbital, an s sublevel, excuse me, we've got an s sublevel, a p sublevel, a d sublevel, and an f sublevel. Within those sublevels, we've got 1 s orbital. In the p sublevel, we've got 3 p orbitals. In the d sublevel, we've got 5 d orbitals. And in the f sublevel, we've got 7 f orbitals. And in this energy level, we can hold a total of 32 electrons. Remember, we calculated that by 2n squared. All right, so let's take a look at our periodic table. Notice here that we've got, on our first energy level, we've got 1, 2 atoms on our first energy level. Notice that helium is number 1, hydrogen is number 1, it's got 1 electron. Helium is number 2, it's got 2 electrons. Moving down the periodic table, notice we see here, energy level number 2, we've got 2 electrons in our s sublevel, and then we have 1, 2, 3, 4, 5, 6 electrons that can fit in our p sublevel. Notice that each atom, as the atomic number increases, that tell you that the number of protons increases, and because these are neutral atoms, the number of protons is going to be equal to the number of electrons. So, when we look now, let's go down to the fourth energy level. That's where things get a little bit tricky. Our D block, notice that there are 10 atoms in each period in the D block. Here, these atoms that we see here. Okay? Now, remember, the D's start in energy level number 3. So when we look here on the periodic table, we have to know that this set of atoms has electrons in the third energy level, starting in the third energy level. Okay? So, as we are thinking about electron configurations, these electrons are housed in these orbitals within sublevels, within energy levels. Now, as we move down the periodic table, notice that we start our f orbitals in our fourth energy level. So when we look down here, these atoms have electrons that are found in the fourth energy level. Okay? Now, we don't necessarily do electron configurations of these atoms. They get to be a little bit difficult. We will focus on our representative elements in groups 1, 2, and well, 1A, 2A, 3, 4, 5, 6, 7, and 8A. And a few we will do in the D block. Some of these transition metals. So now that we know that we can use our periodic table as it represents our table as it represents the energy levels in atoms, we can use it to help us to write electron configuration straight from the periodic table. Let's try a simple atom. Let's look at sodium. Here we have sodium. It has 11 electrons because its atomic number is 11. And so we can count, or we can write our electron configuration based on the periodic table. So counting our electrons, we see we have 1, 2. We have two s electrons in the first energy level. Moving down the periodic table, notice that we have 2 electrons in the 2s energy level. As we move across, notice that we have 6 electrons in the 2p energy level, followed by 1 electron in the 3s energy level. Okay, so what does this electron configuration mean? Let's break each part down. So here, that is N, or the principal energy level. Here, these represent the sublevels. These represent the sublevels. And here, we have the number of electrons in that sublevel. We could expand this electron configuration to show that the 2 electrons are in separate p orbitals, or each pair of electrons are in separate p orbitals, but that's not necessary for what we want to do here. Let's try another one. Let's try one of the transition metals. Let's take a look at vanadium. Oops. It's got 23 electrons, and we can go about writing our electron configuration based on what we see. We know we've got 2 s electrons in the first energy level. We've got 2 s electrons in the second energy level. We've got 2 or 6 p electrons in the second energy level. Moving on up, we've got 2 electrons in the s sublevel on the third energy level. Moving on to the p sublevel, we've got 6 electrons. Notice as we going across, we end up here in energy level 4. Notice here on the outside, we're in energy level 4, and there are 2 s electrons in that energy level. And we know that the D block doesn't start until the third energy level. So as we move forward, we have 1, 2, 3 electrons in the 3D energy level. Now, why this is because the 4s electrons have a little bit less energy than 3D electrons. If we think about it, let's go back to our house right quick. Let's think about our house. If you were filling up the house with guests, how would you rather that guests be filled? You rather that guests be filled in each bed one at a time until the beds get full. Now, when we get up to the fourth and the third floor, notice that the third floor gets kind of crowded after the P room is full. Well, remember that all systems want to have, want to have the least amount of energy expended, right? So the electrons are placed so that there's the least amount of energy that's involved in holding those electrons near the nucleus. So by crowding in electrons down here in the d orbital, that's a little bit more energy than, let's say, putting electrons up here in the fourth energy level. So once the 4s sublevel is full, then we start adding electrons here down in our D energy level on the third floor. This trend continues as we move up the floors, but we won't be doing any electron configurations that go up too much farther than the 4p energy level. Maybe some 4ds, but not necessarily 4ps. Let's do some more practice. Let's do one of these elements over here. Let's take a look at selenium. Notice that selenium, we'll start over here. Selenium has 34 electrons. So we can fill up the electrons based on the periodic table. And I'm going to write them quickly. Notice that we write the 4s. We've got the two 4s electrons followed by the d electrons. And then we have 1, 2, 3, 4 p electrons. And what energy level are we out here? Notice that out here, we're still in the fourth energy level, so we put those there. Notice that as we went along, we filled in electrons just as we were going from atom to atom, right? So there is at some point where we can do a shorthand notation for electron configuration. If we use the noble gas configuration, we can determine if we know what the previous noble gas is, we can use that configuration as a shorthand. So let's take a look at sodium. Sodium is number 11. The previous noble gas is neon. How many electrons does neon have? Well, the number is here, 10. So we can take these 10 electrons here and we can do this notation as neon followed by the remaining electrons in sodium. And we have our noble gas configuration. Let's take a look at selenium. Selenium, the previous noble gas here, is argon. Argon has 18 electrons, so we can count out the first 18 electrons. And that is 2, 4, 10. And we have these guys here. So notice that these first 10 electrons, or these first 18 electrons, represent argon. Notice we're left with the remaining electrons for the remaining electron configuration. So we can write it as argon 4s2 3d10 4p4. Now, when we're thinking about valence electrons, those are going to be the ones found in the outermost energy level, and that is N. So whenever you're looking at valence electrons, you want to find those that are in the highest energy level. So let's take a look at sodium. What are the valence electrons in sodium? Well, if we look at the electron configuration, we notice that 3s, these electrons are found in 3. Let's use a different pen color. Let's use purple. Notice that the highest energy level is 3, so the valence is the highest energy level is 3, so sodium has 1 valence electron, and we know that because it's found in group 1 right here. Let's take a look at selenium. Well, if we find the highest energy level, we notice that that is 4, and if we count the total number that we have 6 valence electrons in selenium. If we go back to our Bohr model, we started off where we said our nucleus was in the center and we had our principal energy levels surrounding the nucleus. For ease of the drawing, I'm just gonna do 2 energy levels. And when we're putting the Bohr model and the quantum model together, we can kind of see how the energy levels are broken down slightly. So if we take a look at each energy level, let's say that on the S energy level, I'm sorry, not the S energy level, on the first energy level, we have an S orbital. It's spherical and it can hold 2 electrons. Let's say this is 3-dimensional, but I'm drawing it on a 2D space. If we go now to the second energy level, we have also an S energy level, but we also have our P energy levels. So they're dumbbell shaped, and we have 1, 2, and 3 in the X, Y, and Z axis. So we can have those 2 electrons in our S orbital, and then we can additionally have those 6 electrons in our p orbitals. If we went out further to the next energy level, where we have n equals 3, we see once again we have our S energy level, and we can put 2 electrons out here, and we also have those p energy levels that extend out beyond the energy levels that were in, or I'm saying that extend beyond the orbitals that were in the second energy level. And notice we can have electrons, 6 electrons out here. See here how this S electron is somewhere within this p orbital space? That's only because we're in 2D, and in actuality, these electrons cannot occupy the same space at the same time. All right, and remember, the orbitals are probability. It's a probability. It's a place where we could probably find an electron in space at any given time. So hopefully this helps you to visualize. I can't draw the d orbitals. They get to be a little bit too complex if I put them all together. Hopefully this allows you to see how the atom gets larger as we end up with more and more energy levels, and also how the S and the P orbitals relate with each other. Hopefully that this short video has helped you to understand writing electron configurations and understanding valence electrons.